Okay, so I'm going to start with a quick sort of refresher of what we were talking about last time. We were talking about Jordan canonical form. We almost finished this this section 5.5, huge section, of course. Started off by talking about diagonalizability, which is a pretty substantial discussion on its own, and then all this Jordan form business, another substantial discussion. So 5.5 is just enormous. So a quick summary starting with Jordan canonical form. What's the deal with Jordan canonical form? It's a consolation prize to diagonalizability. If you want to diagonalize a matrix, but you can't because there aren't enough eigenvectors, the good news is there will always be at least one way to put it into Jordan canonical form. Okay, so what is Jordan canonical form? What are the rules? Well, there are these eigenvalue blocks on the diagonal that have these nice features that connect directly to eigenvalues. Thus, my terminology. By the way, the book, for whatever it's worth, the book doesn't give a name to these blocks. So I kind of made up this name, eigenvalue block. I think it makes a lot of sense. Inside of the eigenvalue blocks, there are these smaller blocks called basic Jordan blocks. Right? And again, there's certain rules about basic Jordan blocks. Okay, what's inside of a basic Jordan block? You know, as again, we turn up the magnification, looking smaller and smaller scale. Inside of the basic Jordan blocks, it's always the same. You've got eigenvalue on the diagonal, and then immediately above the diagonal, just ones, and only immediately above the diagonal. Everywhere else inside of a basic Jordan block, all zeros. Everywhere inside of the eigenvalue blocks, outside of the basic Jordan blocks, all zeros. And everywhere outside of the eigenvalue blocks, all zeros. So Jordan form has a lot of zeros in it, which is super. Zero is a very convenient number. Okay. All right. Saw some examples. Don't forget that what we're talking about here is understanding the underlying linear transformation, which is done by conjugations, aka change of basis, right? And the matrix that we use to do the conjugation, aka the change of basis, has columns that are the basis in question. This basis that I have highlighted, the columns of this P matrix, the basis that we're using for the change of basis, that basis is really what accomplishes our attempt to get the matrix into Jordan canonical form. This basis is what has Jordanized our matrix, you might say, right? And so I like to call it the Jordan basis. Again, the book doesn't give that a name either. Okay. All right. We had this discussion about rearrangements, and you've probably noticed on the additional homework problems that there's at least one. I've forgotten, or maybe there's a couple of them. But questions relating to rearrangements of blocks in Jordan form. And the big idea is to notice that when you rearrange blocks, what you're doing is you're really doing a change of basis. You're really doing a change of basis in which you're reordering the basis vectors and such. Right? So what that means is, and we talked about all the details last time, so I'm just doing a very quick overview here, but every rearrangement of blocks is a change of basis. Therefore, every rearrangement of blocks is a similarity. Right? Conjugation, if you prefer. I prefer similarity or change of basis. So what that means is that even though this matrix A, there's at least two Jordan forms, and I can see them right here. There's multiple Jordan forms, right? Sure, but these Jordan forms are similar. So since what we're talking about is understanding matrices, ignoring changes of basis, we want to get at the underlying transformation. All these similarities, all these rearrangements of blocks, they are similarities, and so we ignore them. Right? So, thus, this theorem right here, the punchline of which is exactly one Jordan form, right? So there's this kind of a sort of a uniqueness of Jordan form, with the asterisk that, up to similarities, right? And Similarities are all rearrangements. So ignoring the rearrangements, aka similarities, it is true in that sense that every matrix has exactly one Jordan form. Okay. All right. Okay. Then we ended on a discussion of eigenvectors. And it turns out, interpreting a matrix, J, interpreting that as representing some linear transformation with respect to some basis, right? And remembering all of our rules from section 5.3 of, how is it that a matrix represents a linear transformation with respect to a basis? Well, the columns are the images of the basis vectors and all that. The punchline is that then for a basic Jordan block, such as that, right, the columns give us equations. That column gives us that equation. That's just a straight read, interpreting a la section 5.3. And this column, that column gives us that equation. Okay, focusing on what we're most interested in here. For every basic Jordan block, notice there is exactly one associated first column that intersects with that basic Jordan block. It is exactly and only that first column that won't have one of these extra ones in it, right? And therefore it is exactly and only this first column that will correspond to this equation that is an eigenvector equation, and therefore we get, corresponding to that column, one eigenvector. Right? So for every basic Jordan block, you can immediately infer one eigenvector. And it's hard to prove, but true, and we're not going to do it here. But this is not just sort of the coincidence of that which we can observe. This is actually really getting at the point. So for every basic Jordan block, there really is exactly one corresponding eigenvector. So said differently, total number of Jordan blocks tells you total number of eigenvectors. If you know how many eigenvectors you have, you know how many basic Jordan blocks you have. And this correspondence is kind of perfect. Okay, so that's this theorem right here. Okay, so this is where we ended last time, and I'm just going to go on now with an example that we didn't quite get to. So suppose this is our Jordan form for some matrix. What can we infer from that? Now, don't make the classic mistake. The classic mistake that a lot of students make is to say, oh, okay, well, then I guess that's an eigenvector. And, well, no, that's not, that's not what that means. That's a column. That column is telling you about the image of one of the eigenvectors, right? That column is telling you this equation right here. Right, so it's not that 400 is an eigenvector. You might say 400 is telling you what you can then subsequently realize is an eigenvector equation. The eigenvector is the vector in the basis, the corresponding, well, of course, this is the first column, so it's the first basis vector. It's that corresponding vector in the basis that J is in terms of. All right, so 400 is not the eigenvector. V1 is the eigenvector because 400 is in the first column. Yeah, everybody good? So along those same lines, 004 is telling you this equation. Right, this is the third column, therefore it's telling us about the image of the third basis vector, and therefore this resulting equation says that V3 is an eigenvector. How are we doing? Everybody on board? Okay. Notice the connection to the basic Jordan blocks now. The basic Jordan blocks, let's draw our basic Jordan blocks in this picture. Let's see here, let me come up to there, and we'll go ahead and zoom one more. Here we go. The basic Jordan blocks are there and there. And notice that these two columns that give us eigenvector equations Right? These two columns that give us eigenvector equations. These two columns that are all zeros except for on the diagonal. Those columns, each one of them, corresponds to the first column that intersects a given basic Jordan block. This yellow column here, that's the first column that intersects this basic Jordan block. This orange column, this is the first column that intersects that basic Jordan block. So for each block, we get exactly one eigenvector per these equations. Oh, hang on. Per these equations. Yeah, yes?
Then wouldn't the basis do V1 and V3 since V2 can be expressed as like a multiple of V1 and V2 and V3?
No, it can't.
Like
What the?
V2. Does that make V2?
I'm sorry, say again?
Like V2 can V2 be expressed as 1 V1 plus 4 V2? Oh, V2, sorry.
V2, that's the thing. Yeah. Right, yeah. Okay. Cool. Anybody else? Everybody happy? Okay. All right. Let's see here. Okay, so reminder, and I've been commenting on this as we go along. These theorems about Jordan form, we're not going to prove them in this course. They're too hard to prove in this course. In Math 221, right, the sort of the math major version of linear algebra, they might prove this theorem. But it's a pretty substantial proof. And by the way, two theorems, to prove that every matrix can be put into Jordan form. That's a hard thing to prove. And secondly, that up to rearrangements, Jordan form is unique. That's another hard thing to prove. Okay, so anyway, not going to do that in Math 216. So you're absolved of any responsibility for that. Next question. How do you find this basis, right? So we've talked about what the Jordan form looks like. We've talked about once you have the Jordan basis, what can you infer about, what the linear transformation does with respect to that basis. We've talked about what to do with it. We have not talked about how to find it. How do you find the Jordan basis? And that's another thing. It's, we can't really do that in general. It's hard. It's beyond what it's worth the effort to put into in Math 216. So nevertheless, there are some situations. Every so often you get lucky. First observation I'll make is that diagonalizing is actually Jordanizing. Right? So diagonalization is a special case of the Jordan form. If you think about it, let's look at an example. If I have a diagonal, let's say 3, 3, 5 as my diagonal matrix, this diagonal matrix is in Jordan form. There's an eigenvalue block. Here's another eigenvalue block. And the basic Jordan blocks are all just 1 by 1. Right, so a neat observation. You might have to rearrange the diagonal entries to get the repeated eigenvalues. Maybe you might have to rearrange those blocks to kind of get them together to make an eigenvalue block. But diagonal form is Jordan form. And we know how to find the Jordan basis in this case because here we're talking about diagonalizing. We know how to diagonalize. That's eigenvectors, right? Find a basis consistent of eigenvectors. So, like I say, sometimes you can do it if you get lucky. Here's another situation where stuff works out pretty nicely. This won't happen every time, but yeah, sometimes. So, by the way, here we're not going to be able to find the basis, but we'll be able to find the Jordan form. Suppose you have a matrix with that characteristic polynomial. By the way, characteristic polynomials are easy to write down. Right? We've done that a bunch of times. You just kind of multiply it out and find the characteristic polynomial. We have a root 1 with multiplicity 2. And that tells you right there, that tells you a lot of information. That tells you, because the multiplicity is 2, that tells you we have a 2 by 2 eigenvalue block. With diagonal entry being the eigenvalue 1. and just play the game and think to yourself, how many different ways can we write down a 2 by 2 eigenvalue block? There's only so many different possibilities of Jordan blocks that can fit inside of this 2 by 2 eigenvalue block. In fact, there's really only 2 possibilities, right? By the way, with 1 on the diagonal. The only 2 possibilities are that we have a couple of 1 by 1 basic Jordan blocks, or that we have a 2 by 2 basic Jordan block. So right off the bat, right, I've got this reduced pretty well. Oh, by the way, of course, we also have this, the eigenvalue. The eigenvalue of 3 here with multiplicity 1. That you see there, that gives us this 1 by 1. And of course, there is only one way to have a 1 by 1 eigenvalue block. And that's to have, well, obviously, of course, the only 1 by 1 basic Jordan block inside of it. So, grand total, just by looking at the characteristic polynomial, there's only 2 possible Jordan forms. Now, how do I distinguish between these? Well, we have this result from a few pages back here that for every block, there is a corresponding eigenvector equation and therefore a corresponding eigenvector. Right? So if you know the number of eigenvectors, you know the number of basic Jordan blocks. And that applies just fine and dandy right here, this situation. Whatever this original matrix was, find the eigenvectors, right? We've already got the characteristic polynomial. We already know the eigenvalues. Just go through and play the game. And if this eigenvalue here, if that eigenvalue has 2 eigenvectors, then there's 2 eigenvalue blocks, namely that. And if there's only 1 eigenvector, then there is only 1 basic Jordan block, namely that. So, like I say, sometimes you get lucky. Okay. Last thing I'm going to talk about is how to sort of, take this to higher levels. If you know a characteristic polynomial, how many different possible Jordan forms are there? And this is really just an observation of a sort of a mathematical coincidence that this thing called the partition function comes up. Be curious, little function. Just quick definition of the partition function. Partition says how many different ways are there to add up positive integers to get a certain value. So what we see right here, there's 5 different ways to add up positive integers to get 4. And we ignore rearrangement. So 2 plus 1 plus 1, that's the same for our purposes as 1 plus 1 plus 2. Yeah. So 5 different ways of doing this. This is called so we would say the partition value of 4 is 5. Okay, so the observation I want to make here is that if you have a multiplicity of 4, that means that you have a 4 by 4 that's pretty ugly, isn't it? Let me try that again. If you have a 4 by 4 eigenvalue block, because of this multiplicity of 4, how many different ways are there to put Jordan blocks on this inside of this eigenvalue block? Well, it could be the whole thing all at once, or it could be a 3 by 3 and a 1 by 1, or it could be, oh gosh, am I going to be able to erase? Could be a 2 by 2 and a 2 by 2, etc. Right? Every different possible way that you can put basic Jordan blocks inside of this 4 by 4 eigenvalue block corresponds to one of the ways to partition 4. Okay? So you can just go through and play this game. Let's go through and see how many different ways can you add up positive integers to get 4. There's 5 different possible ways to do that. Thus, for this 4x4 eigenvalue block, we've got 5 options. And then, same story. For the 3x3 eigenvalue block there, well, here's partition of 3. There are 3 different ways to do that. Right, so there's 5 different possible forms. For on the left, you might say, there's 3 possible different forms. On the right, grand total, mixing and matching, there's 15 possible Jordan forms for this matrix. Everybody on board? Okay, so that's the last we needed to say about Jordan form for a while. We're going to move on now to the, I'll say, next chapter. We're actually doing a little bit of a jump out of order here. We're going to start with chapter 9. Let me give you a quick comment on my motivation for this. I mean, why, after chapter 5, you would think we'd go straight to chapter 6. That would be a perfectly reasonable thing to do. The thing is, chapter 6 is about differential equations. And we're kind of we've got a certain amount of linear algebra momentum going on here, and I think it makes sense to get our linear algebra done so that we have as many linear algebra tools as possible to work with when we then, for the last time, make a switch and go into talking about differential equations to finish the course. Right? So it's not a big deal, but I am going to go ahead and jump up to chapter 9. Okay. So, do y'all remember dot products? I hope you remember dot products. So, dot products is a thing in Rn. Here's the formula for it. Right, a bunch of different facts about dot products in Rn. I've got a long list here of facts about Rn. About the dot product in Rn. So, here's what I'm calling some facts. Here's some more facts, and here's still more facts. Turns out there's some interesting distinctions about these facts, so that's why I have them separated into 3 groups like that. We'll come back and talk about those in a moment. I do want to call your attention very quickly to this one. The book writes this a little bit differently. In fact, the book writes down a different property. This 4th property that I have listed. The book writes down a significantly different, but very similar looking fact. And it turns out that it makes a difference. The way the book does it is a little problematic for certain applications that we're going to make use of, and so I'm going to insist that we do it this way. You'll notice that in the book, they don't require that the dot product of a vector with itself be positive. They just observe, slightly weaker statement, that a dot product of a vector with itself is only 0 if you're talking about the 0 vector. They kind of leave open the door to the possibility that maybe it's negative. And we know it isn't. Right? Well, anyway, it turns out that's going to make a difference. So anyway, heads up on that difference. Okay. So with this in mind, let me remind you of some things that we did back in chapter 2. So in chapter 2, one of the first things we did is we defined vector spaces. Right? I want to remind you what the thinking was there. Chapter 2, we started to notice that there were different kinds of sets of realms of consideration, right, that behave a lot like Rn. Right? Consider the collection of all functions, real-valued functions. You can add them. You can multiply them by scalars. It's just like when you add vectors in Rn. It's just like when you multiply vectors in Rn by scalars. It's, behaves really a lot like Rn. Functions behave that way. Certain specific subcategories of functions behave that way. Matrices behave that way. Solutions to differential equations behave that way. This is a very partial list. There's lots and lots of examples of sets of things that, in a lot of important ways behave just like Rn. Okay, so what we did with that observation was we said, look, I don't want to have to deal with each of these realms separately. They all kind of behave pretty much just like each other. Let's define an abstraction called a vector space. we define a vector space based only on how things behave, not at all on what they are. Right? So again, if you look back at the definition of a vector space, it never says these things in a vector space have to be of a certain, no, not at all. Right? Just, can you add them? Can you multiply by scalars and do those operations behave like those operations on Rn behave? Okay, so we created an abstraction. We proved a bunch of theorems in the abstract. We made definitions. We proved theorems all in the abstract, proving theorems about vector spaces. And what we find then is that we are heavily armed at that point, right? If you ever encounter a vector space in the future, then, even though you just encountered this vector space for the first time, well, yeah, but you've got a long list of tools and theorems to work with for free instantly. Okay? It's a very powerful idea. And then, of course, we did, as it happens, kind of coincidentally encounter a new vector space, right? Set of solutions to differential equations. We used all of this linear algebra of vector spaces to help us solve differential equations. Okay, so that abstraction, the vector space abstraction, that's a good abstraction. We did some nice things with it. And it is not the only kind of abstraction. That strategy of abstraction is useful in lots of different ways. And so what we're about to see is a new kind of abstraction. It's different than vector spaces. And it has different applications than vector spaces. But it's got a lot in common in the sense that, look, we're not going to talk about what these things are. We're just going to say, look, anything that behaves according to certain rules as sort of motivated by kind of, familiar things like Rn, anything that satisfies the rules is, an example of one of our abstractions, and look at all the theorems that we've already proved. So that's what's about to happen. Here's what it is. It's called an inner product space. So what is an inner product space? Reminder, don't look for what the objects are, right? The whole point to the abstraction is that we want to refrain from saying what these objects are. The less we say about what they are, the more broadly this abstraction could apply in ways that we haven't even thought about yet. Right? Okay, so who knows what these things are, but here's the rules. You start with a vector space. We already know what that is. Keep in mind, on a vector space, you have two operations. You have an addition. Right? So when we say V is a vector space, that means that there is an existing addition operation on that vector space. There is an existing scalar multiplication operation on that vector space. Okay, now, furthermore though, suppose we have an additional operation. And the convention, it is a weird convention, I'll confess, but we use triangular brackets. Instead of putting like a little symbol in between the two things, triangular brackets. It's very common. So anyway, we're just going to get on board with the common notation here. This operation, satisfying these four rules, that operation is called an inner product. And when you say that you have a vector space along with an inner product, then that vector space is now a souped up, more powerful, more sophisticated version of vector space called an inner product space. So that's what it is. It's a vector space with an additional operation that obeys certain rules. Yes?
So will this abstraction only apply to vector spaces?
Yeah, that's right. So that's first rule. It's if you want to have an inner product space, you have to start with something that's already known to be a vector space. Absolutely. Yep. Okay, now, where did these four operations come from? Did I just make this up? Right? Well, no, of course not. When we were talking about vector spaces, we were thinking Rn, right? And we were probably thinking R3, right? Because that's how we tend to, we think about vectors in three-dimensional space because that's where we live. So we were thinking about R3. So where did this additional function, this inner product function that I have highlighted in purple, where did these 4 required properties come from? I ripped them off from the dot product. These 4 properties of the dot product from R3. Rn, R3, take a pick. Okay, so roughly speaking, in the same sense that when we say a vector space is something that behaves kind of like R3 with respect to addition and scalar multiplication, an inner product space is something that behaves kind of like R3 with respect to addition, scalar multiplication, and dot product. It's just a rip-off of the idea of a dot product. Yeah, everybody okay with that? Is any questions on that? Okay. Yes, please.
So with the list of properties, the first one I get the second distributed. The third one, does C specifically end up getting multiplied by the first thing, or would it also could you also do the second one?
That's a great question. Let me, if I may, I'd like to procrastinate on that question for a couple of minutes. It's a fantastic question, and I will answer it. It's just going to really segue very nicely into my lecture in about 2 minutes. Yep. Anybody else? Okay. Okay. So let's see some examples of inner product spaces. The first one is the freebie. So Rn itself. Here, let me color code correctly. Rn, I claim, is an inner product space. But keep in mind, we already know that Rn is a vector space. That's old news. Again, it was our model for vector spaces. Furthermore, the dot product, we already know satisfies these 4 rules. See the previous page, right? These are the first 4. This is a total ripoff. That's why we wrote those 4 properties down, because dot product satisfies those 4 properties. Yeah.
So would you say that the dot product is the inner product function in Rn? And like
Yes.
In other vector spaces, there's going to be another function.
Yes, that's exactly right. And in different vector spaces, let me say it a little bit differently. For different vector spaces, if we want to try to turn them into inner product spaces, we're going to have to use a different formula to kind of play the role previously played by the dot product. It's going to have to be something else, though. Yeah.
So just like addition, we have to define like a new addition, and multiplication, we have to define a new.
Yep. Yep. That's right. That's exactly right. Okay. All right. Okay, so here's a highly non-trivial example of an inner product space. The collection of all continuous real-valued functions defined on the closed interval from A to B. So you all remember this guy. This is from 2.2. This is a subspace of what we wrote as capital F. So this is a vector space. We have an addition inside of C. We have a scalar multiplication inside of C, right? So this is a vector space. Satisfies all the vector space properties. And now I'm going to attach to that a new operation. This is the inner product operation that I claim we're going to use. And by the way, anytime you claim you've got an inner product, you've got to make sure that it actually is an inner product. So technically, I owe y'all proofs of these first 4. Well, these 4 properties. It's got to satisfy all 4 of those properties for me to be able to say I claim this is an inner product. Let me hit pause on that for just a moment. I claim that all 4 properties are satisfied. So you can check that does work. And altogether here we now have a new inner product space. So C attached with this inner product is no longer just a vector space. Now C is an inner product space. How are we doing? Okay, now, so let's go back to these proofs. There are 4 proofs here. The first 3 of these proofs are very straightforward. And these are fantastic exercises. Just write it down. Write down the left side. Right, plug in this formula for what this this operation is, and then do what you already know how to do with calculus, right? We already know various properties of integrals, and you can confirm that those first three properties, it's just plugging in. It's very easy little proof. So make sure you can do that. Those would be fantastic practice problems. As usual, if you get stuck, you're not sure how to get started, if you get halfway through and you're not sure where to go, let's talk in office hours. You can ask in discussion section, ask a classmate, whatever. But give those a try. Good problem. This fourth one is not that easy. This fourth one requires some careful work. It requires taking specific advantage of the fact that these functions are all continuous. The fact that they are continuous is necessary to do that proof of property number 4. So again, give that a try. Right? See if you can do that. But note that you're going to have to make use of the continuity. And if your argument doesn't make use of the continuity, then your argument's not complete. Okay, so give that a try as well. Okay. And again, come talk to me in office hours if you get stuck. All right. For reasons that I won't talk about here, this inner product has a name. This inner product is called the L2 inner product. There's a great reason for that. We just don't have time to fit that in. But so two things. First of all, henceforth, I will very often just refer to the L2 inner product. And so you have to make sure that you know when you hear me say L2 inner product, I mean this. Okay? Second thing. When we're talking about C, if it is not explicitly specified to the contrary, if we're talking about C as an inner product space, this is the inner product that should be assumed. This is the default inner product on this that you attach to this otherwise vector space, now inner product space. Okay. All righty. Okay, here's a fact that we've never stated before, but this is a pretty believable fact. Dot product is not preserved by change of basis. So what I mean by that is this right here. If you were to take a couple of vectors, I think this is highly plausible. If you take a couple of vectors and write down their standard basis coordinates and dot those coordinates in the usual way. On the other hand, if you were to take those vectors and write their coordinates with respect to some totally different basis, you're going to have totally different coordinates, and then when you dot those, I hope no surprise, you're going to get a totally different value. Right? So, of course, change of basis does not preserve dot product. Easy to find examples of it. In fact, it's fairly hard to find an example of a change of basis that does preserve the dot product. So, in some sense, it's almost true to say pick any basis. Odds are it's not going to preserve the dot product. Okay. All right, so why are we mentioning this? And that is because even though this formula is not the same as standard basis coordinates dot product, it is itself a different inner product. So, let's say it a different way. Even though this change of basis dot product doesn't give you the answer that you were expecting, it's not useless. This is a perfectly interesting, perfectly acceptable inner product that has all the algebraic sort of, stripes, if you will, of a regular dot product. It's just not equal to the original regular dot product. Okay, so this is something that, you can check all four of the properties. By the way, you're going to have to, in exercise 9 for section 9.1, the way exercise 9 is written is not exactly like this. It's written in a different way. But what I'd like y'all to do, when you're thinking about exercise 9, when you're working out exercise 9, think about how that connects to this example. And it turns out that this inner product written here is equivalent to the inner product from exercise 9. Turns out it's the exact same thing, just written in a different way. So anyway, make that connection when you're doing exercise 9. Okay. All right. All right. So now a quick reminder. Here's what we were talking about with inner product spaces. We started with a vector space. We attached to it a new operation called an inner product. The rules for an inner product are these 4 properties here. Where did these 4 properties come from? These 4 properties came from these 4 properties of the dot product. So, a very plausible question to ask is, what's so special about these 4 properties? Why didn't I include all 7 of these properties? After all, if I want something to behave like a dot product, well, dot products behave like this. Why is it okay for dot products for new inner products to not be like dot products with respect to these properties, but they have to be like dot products with respect to these properties? Why the distinction? Right? Reasonable question. There's a great answer, and that is that it's not that I don't want these properties to be true. I do. I do want these properties to be true. And they are. These 4 properties here imply those 3 additional properties. I don't have to require these 3 properties. They're free. Right? Once you've checked that your candidate inner product behaves these 4 properties up here, it immediately follows that these 3 properties here are satisfied. Right? So, for example, let's suppose once you know that these 2 properties here are satisfied, properties 1 and 2, so you can switch left and right. You have commutativity, right? And you know that your candidate inner product has what you might call a right side distributivity. Well, if it's got right side distributivity, just switch it, right? Then it's got left side distributivity. So these 2 properties automatically give me that one. Right. So once I've checked properties 1 and 2, I don't need to bother checking property 6. Property 6 is free. It has to follow. I've already checked 1 and 2. Everybody on board? So when you make a definition, you want to make your definition as lean as possible. You don't want to have your definition require that you're checking stuff that you've already checked. That's just make work, right? So keeping our definition as lean as possible. These here make up our definition. And these here are free. Everybody on board with that? Any questions? Yes?
Is it ever more convenient to, find one property over another? So, for example, finding that you can write stuff?
So you're wondering if maybe, might there be a circumstance where it would have been more convenient to use 6 instead of 2? Yeah, maybe. And sadly, though, when we make a definition, we have to pick one definition and stick with it. And we can't. I said it would be very complicated for us to make an inner product. An operation is an inner product if it satisfies any of the following 10 combinations of these 7 rules. It would just be kind of a pain, right? So we just we make this definition arbitrarily, and we take these as free, kind of arbitrarily. Yeah, right. It's a very reasonable question, though. Yeah. Okay. So there's another additional fact. We didn't write this out about dot products. In Math 212, they don't talk about linear transformations, and so the following wouldn't really make any sense. But this is more sort of lingo of linearity that you guys should be on the lookout for. We'll say that inner products are linear in each entry. Now, there's that word linear, right? I want to remind you of the advice I'm giving about the word linear. When you see the word linear, what that means is there is a linear transformation somewhere in the picture. Identify what that linear transformation is, And then you can interpret that what the speaker said when they said linear in each entry. You can infer the meaning of that by realizing that is a linear transformation. So here is the function in play here. The function is inner product with W. Inner product with W is a function. You give me a vector V, I can do an inner product with W. Right, so this is a function that you can apply to any input vector. And notice that what this equation says here is that if you put a linear combination in to that function, then you get the corresponding linear combination out from that function. Or said differently, you can do the linear combination before you plug into the function. You can do the linear combination after you've plugged into the function. Same thing. Okay, so inner product with W is the function. What goes into the left side of the inner product is the input to this function. So when we say that this inner product with W is a linear transformation, another way to say that is whatever you put into the left side of an inner product, you have a linearity there. Right, so we would say here that what this equation that I've got highlighted right now says that the inner product is linear in the left entry. Linear combination in, linear combination out. Okay, so likewise, this is what we mean by linear in the right entry. The function in question is inner product with W. That's the function, and notice linear combination in, linear combination out. So the inner product is linear in the right entry as well. Yes?
Does this work if they're both?
No, one entry at a time. One entry at a time, yeah. So it's kind of like multilinearity was in that sense. Yep. Right. Okay. All right. Okay, so going back to our list, we had this long list of properties that dot products satisfied. I broke them up into three groups. This group, the distinction that this group of four properties of the dot product had was that these make up our definition. Right? The distinction that these four properties have is that these are, as a result, free and automatic, and I don't have to check them. Those are freebies once you've checked the green ones. Okay, so what about the next group of operations here? What's the deal with these? Why didn't I make those part of the definition? Do those come along for free? Is it true that everything that satisfies those first four green properties up there, do they necessarily have to satisfy these properties? And the answer is, I don't really understand the question, is the answer to the question. So, let me expand on that. So here's the thing. We're asking about the dot product, or a potential inner product, and notice that these equations down here make reference to magnitude and angle in various places. Right? So these four properties are not just properties of the dot product. These are properties of other things as well, right? So if you want to know, does an inner product necessarily have to satisfy this rule? Well, I don't know. What do you mean by magnitude? We haven't defined magnitude yet in some random vector space. Right? We haven't defined angle. What's the angle between two matrices? Right? So I don't know how to answer the question because we haven't defined these four questions yet. So we can't just say that they're automatic, but we also can't really decide immediately if they're true. So what we're going to do here is we're going to take a completely different point of view. The fact that these are undecidable allows me to do the following. I'm going to take this equation here. Let's see here. Well, I'm going to take this equation here and call that the definition of a magnitude. Right? In the same way that you can define magnitude in Rn as, well, magnitude is the square root of the self-dot product of a vector. I am likewise going to define magnitude in an inner product space to be the square root of the self-inner product of a vector. So, now we have a new concept, right? We have this concept now of magnitude, and very similarly, we can define angle. I'm going to define, right? There's no pre-existing notion of what does it mean to talk about an angle between two matrices, right? So I'm going to define, weird though it may seem, the idea of an angle between two matrices. Give me an inner product. All these things I can compute. Take the arc cosine. That's my definition of the angle between two matrices. Yeah.
With the square roots of things, do all inner products give two constants like the dot product does?
Do all inner products?
Do they put out a?
Oh, yes, they're all real valued.
Okay.
Yes, that's right. Yeah, absolutely. Yeah. Okay, I'm out of time. See y'all on Friday. We'll pick up here then.